Is yeah, okay. So what I want to discuss today is the personalized federated learning, and in particular, what we're gonna look at is how to kind of remove one of the more serious issues within federated learning, or when you want to train your model in distributed setup, which is data heterogeneity. So this is a joint work with Konstantin Mishenko, Rustem Islamov, and Eduard Gorbunov. Konstantin is in Samsung Research. Rustem is currently a PhD student in University of Basel, and Eduard is a postdoc with us, and also he's in the audience. All right, so let's just discuss the setup. So as was already said, we consider a standard federated learning setup, whether that's the cross-silo federated learning, where we have different institutions. You can think about hospitals that want to collaborate in order to have, let's say, some intelligent agent to help you to do the diagnosis. But the thing is, they cannot directly share their data because this data might be private. Also, one of the things that we're also looking at is the cross-device federated learning, where now devices are some constrained devices, such as mobile phones, where we want to train some global model. That might be a recommendation model that we want to train on those devices, but also use it on them. So the deployment is also one of the challenge. As was already discussed, especially in Eric's talk, so the standard objective that we tend to optimize is we're just trying to find a global model that I'm going to denote X star, such that when we have local loss on each client, that this X star acts as a good approximation to the true minimizer for each local client. So there are certain limitations to the global model, in particular if we assume that there actually is data heterogeneity. So this might be often very restrictive, and in many cases it might not even exist. So think about this simple problem where you just want to do the next word prediction, where actually the next word's going to be underlying on the person or client that just wrote the first part of the sentence. So in order to kind of remedy this potential issues, a lot of work was done on fine-tuning and personalization, and in this talk I'll focus on the second part. So how the objective then changes when we have the personalization. So instead of trying to find one good global model, what we will try to do is we will try to find a good X star for each single client, such that that X star is as close as possible to the true minimizer for the client. But in order to benefit also from the personalization, we somehow have to link them together. One of the most popular approach might be meta-learning, and I guess some of you in the room already have some work on this. Also, another potential way that I will more focus on this talk is the partial personalization. So what's partial personalization is, we're going to have a split where we have part of the model that's going to be global, and then we have a part of the model that's going to be personalized and that's going to be unique to given client. And then what's our aim is we try to find such a good global model that when we personalize well, we're essentially going to resolve the local problem. And the motivation here is that if we get essentially the split right, then we should also generalize well and have essentially the benefit of collaboration comes from the theta star here. So standard ways how to achieve that. What we can do, for instance, we can personalize the input layer if we assume that there is a lot of heterogeneity that's coming from the input itself. Also, when there is a heterogeneity that comes from the output, we can also personalize the output layer. But also another, I think currently very popular approach is to include some adapters. So we would have some adapters that are local to each client that will personalize our model, and very common way to personalize model, especially for language models, might be LoRa adapter. Okay, so with this, this is general setup, and now comes the main contribution of our work. So when we look at this partial personalization framework, we wanted to see whether you can actually benefit from partial personalization. And how we think about that, we think about the partial personalization as some kind of over-parameterization, and that's what led us to propose this over-personalization that I'm just going to present in this slide. So first, kind of the motivation, what we have here is for machine learning, for general machine learning or centralized machine learning, we know that kind of over-parameterization can help us quite a bit. But the thing is, for instance, when we have a data heterogeneity in terms of, let's say, the prediction, so giving some input giving the input, the output of the model should differ across the client, that automatically limits you that you cannot achieve the over-personalization globally. So that automatically you cannot use the global model just like that, because it's not going to have a property that we can actually achieve zero loss. So how to go around that is what we call this over-personalization. So what you have here, we assume that what we have is split such good enough that what we can achieve is, okay. All right, so what we can achieve is that we have a global model. Then if we properly solve this local adaptation, then what we assume that there actually exists such global model that can exactly solve a local problem at each single client. And with that, what turns out are the great implications of this, that if you get the personalization right, then you can achieve zero training loss for each client. And also another thing is why we frame this as an assumption. This is actually kind of as general as over-parameterization, because you can always achieve that. If you have a big model that has enough capacity, then essentially if I just say that every single parameter is local, then I'm going to achieve this one. Although actually like the problem in practice will be to find the right balance between the local and global models. This is not something that I'm going to discuss. This is something that we would like to approach as a future work. But what I'm going to show you is like once you have this nice property, that essentially it almost acts as an over-parameterization for federated learning. All right, so with this, once we have the notion of over-parameterization, we can also introduce this new objective that we're going to focus on. So our goal is to find such global parameter such that this operator equality can be zero, where this operator is defined as a gradient with respect to the first part of the split that we want that to be zero. And with this, essentially, what is this objective right here? So that objective, what we're trying to do is just we try to find a first-order stationary condition for this over-parameterized or over-personalized objective. How we're going to solve it is we're going to use the algorithm that we propose here that we call fine-tuning followed by global gradient, or FFGG. So what you can notice that the algorithm looks pretty much as the standard method that we would use for federated learning, where the difference is that what we're going to do first, we actually do not just take a single gradient step, but first we're going to solve the local subproblem, where the local subproblem is just to find a good local adapter considering our current iterate. Once we have that, we just evaluate a single gradient, and that's what we're going to use as our update. So with this, what you can notice here that this algorithm has a quite nice property. It's still stateless, so we can also deploy it for cross-device federated learning, and we're also going to show that if you do, so here, that you're actually like doing more and more of this local work, you're actually going to get a better convergence. So you're going to benefit from more and more local work, which is not always the case in federated learning due to the data heterogeneity. When we look at the theory, so this is what kind of brings us to the benefits of overpersonalization. So if we just look at our convergence of this operator, so it goes to 0 OS as a deterministic algorithm, despite that we do the sampling of the clients. And the reason for that is that we have this overpersonalization property that is essentially equivalent to overparameterization in general machine learning. And what is the assumption that we make here? That we assume that this operator is co-coercive, which you can think about as a generalization of convexity and smoothness. So, and here, that's something that I hide here. So essentially how the convergence would look like if you don't do enough local steps, so you would have some term that you can only reduce with the extra number of local steps, but if you do enough local steps, then you can actually get just a deterministic convergence. So the nice implications of this ones are that once you have overpersonalizations, there is no any notion of heterogeneity that's going to appear in the rate. Plus, what we also can show that once we have overparameterization plus co-coercivity, then you can actually see the benefit of cooperation. So firstly, what I said is that the conditions that we solve are only like the first order stationary conditions of the original problem, but we can also show that if overpersonalization and co-coercivity holds, then you actually solve the problem. Also, what you can see is that if you solve this problem, you actually solve the original problem. Therefore, if you have a new client that that just joined, what they can use, they can just start with the parameter theta as their good global model, and all they have to do is actually, they just have to fine-tune this W, which was the local parameter, in order to get the best performance. And let me just quickly finish with what was a part of my title, which was breaking the curse of heterogeneity. So how actually this, so it's essentially this overpersonalization where we show that it does solve some of the kind of important issues with federated learning in general. So first of all, when we look at Byzantine robustness, which is a standard problem in federated learning, as federated learning is a collaboration among mutually untrusted clients, then this would be very easy target to poisoning because anybody can join. But the thing is, if you do personalization right, then we can show that you can actually run just standard Byzantine robust algorithm, and then what cannot happen is that your Byzantines would just simply hide in the noise. So actually for that, once you have personalization, you don't need momentum, you don't need any variance reduction, and you get the right benefits. The same goes for asynchronous learning that Eric was talking about. So now the thing is, if you get this all right, then we know that asynchronous SGD, well, in order to analyze it well and provide the proper convergence, we have to assume that the data are somehow homogeneous. If that's not the case, then theory is very complicated, and we cannot even guarantee the convergence to the exact solution. Once you have the overpersonalization, you just apply this algorithm that I just showed you, and you can converge to the arbitrary, for even arbitrary heterogeneous data if you do the personalization right. And let me quickly just show you the experiment. So first, it's just a simple quadratic that follows our theory, where we show actually that you benefit indeed from the local steps, and as you increase the local steps, you get better and better. And also when we try this on some real-world data set, that you can see that essentially if you do the adaptation right, then you get the state-of-the-art performance, and even with the comparing to the best model, you are either on par or significantly better due to the way how we construct the algorithm. All right, so let me just quickly go through the conclusion, where what we propose is the new kind of personalization framework, where we propose also the new algorithm that can be stateless. We can show that local steps probably help, and we can also handle the heterogeneous data where this key was over-parameterization, then can help us to remove the effect of data heterogeneity. And still the key limitation, what stays is like how to do this well in practice and what's the right split of the parameters that we should use. All right, thank you. If you want to check the papers on archive.
Thanks so much, Sam. Any questions?
Co-coercive functions which are not gradient of convex functions. Do you know examples? Do you know example of co-coercive functions which are not gradient of convex function? Or?
So here, essentially, it's for us, it's not necessarily just a it's not just a gradient because we assume this co-coercivity. I think. Okay, can I go back? Yeah. So we assume here so here we assume the co-coercivity with respect to this operator, like FM, but that FM actually, it's not only like the operator in the first one, but it also has this other term where we have to do the proper personalization. So it's not directly like just a gradient, but yeah, but going back to your question, I do not know any examples. But maybe Edward, I think he is.
My question is it easy to check? For example, you mentioned, for example...
whether that's holds? Yeah, so we have actually a couple examples that, in which, yes.
Going beyond the convex problems, or...
Sorry? Yeah, yeah.
Any other questions? I had a question. Is it repeating? No. So, you mentioned one of the application is that you can recover this ground truth theta and the parameter theta. Do we know if we can actually recover the ground truth theta? Because each FI is looking at only like a part of it.
I mean, each FI is looking to exactly the same one, right? I mean, that part of the model, right? Like you have this, and correct me if I understand your question well, that, I mean, every single client, let me just go maybe back to the algorithm.
So yeah, maybe I can clarify a little. So what I mean is each algorithm, each client is looking at the personalized version of the theta.
Yes.
But potentially there is one global theta which is like the best theta to personalize from.
Yeah.
Do we know if we recover that theta as well?
So I mean, under the assumption, every theta that you find, like under the assumptions that we make, every theta is the right one. For like more general setup that we cannot directly guarantee that, but I guess, I mean, if you design your algorithm well, and the thing is here we do only take a single gradient step, so it should be the case that it should be extendable to more general setup, and I believe that if you kind of set your assumptions straight, even in the more general setup, you can exactly recover that.
If there's no questions, let's thank Sam again, and we'll break for a short coffee break now for 20 minutes.